Swayam Prabha. Digital India. Educated India.
Welcome everyone to today's class. So as you recall, we were discussing the key exchange protocol, a very famous one by Bennett and Brazard, and this is famous why? Very good. So it provides information theoretic security. So this is its main claim to fame. All right, and we talked about the protocol yesterday. We'll discuss a little bit more about the security today. Although as I said, I will not do a full proof in class, okay. So, let's recollect the protocol. So, these are the steps we saw yesterday. So, Alice will choose a string of random bits which she wants to communicate, and she will choose a random basis in which she will communicate this. And the idea is that if I don't tell you which basis I am going to use, then in some sense you don't know how to measure. Right, and if you measure in a random basis, then you will disturb the state and you will be detected with high probability. This is the whole idea. So that's step 1. So you choose a bunch of bits A1 to AN, and you choose another bunch of bits B1 to Bn, except that the B's now represent the basis. So for 0 we will say computational basis, for 1 we will say Hadamard basis. Okay, okay, good. So now having chosen these bits and the basis, Alice transmits the quantum states accordingly, right. So the choice of B will tell her which basis to use, and then she will use, if her bit is 0, she will use the first basis vector, and if the bit is 1, she will use the second basis vector, some such canonical encoding, and she will send these quantum states. Then we discussed that Bob, when he receives them, either he can wait until he acknowledges the receipt and she says, she tells him which basis to use, or if storing these quantum states is a problem, he can choose his own random basis and measure them, and with in expectation half of the choices will be correct, and he will tell her which basis vectors which choice of basis he used, and this will help them to reconcile. They can discard the bits that did not work, right. And then we also said how this does not prevent a person in the middle attack, right. So Eve sitting in the middle, she could mess with everything. I mean, whatever she receives, she could mess with it and send it across to Bob, and this is something which they will never catch. So we had a third step, which was that they also choose some random positions and actually announce the values that Bob measured for those positions, right. So this helps to figure out if there was any tampering in the middle or not. So this was roughly the protocol, and I mean, if we are having Bob measure in a random basis, half the bits we have to throw away that way, it seems quite bad. It is, but I mean, so far this is a feasibility argument. And then after that, another half of them you have to discard because you have announced your bits publicly. So you cannot use them as part of the shared key, right. So in the end, if all goes as per plan, then they get n over 4 shared bits, right. So in today's class, we will talk a little bit about the security of this protocol. Okay, and as I said, we'll just think intuitively about what possible attack strategies Eve could have and how those will play out. We won't do the full proof. So a first thing to notice is that mixed states are relevant here. So if I want to transmit a bit 0, then with probability half I am transmitting 0, and with probability half I am transmitting plus, right, and for 1 similarly. So it's a mixture of 1 and minus, right. So with probability half I will do all these. So now if Eve is receiving this, I mean Eve is sitting on the channel and listening to this, what is her best strategy? What do you think? I mean, what could she do? So let me just write this, okay. So to transmit 0, classical bit 0, right. To transmit bit 0, I send 0 with probability half and 1 plus with probability half, right. And to transmit bit 1, I am going to send 1 with probability half and minus with probability half. Okay. So the main thing that we are trying to demonstrate now is a so called information disturbance trade off. What does this mean? I mean, if as an adversary I mess with this transmission very little somehow, right. Like for instance, in the end only half the positions will be revealed. If I only messed with 1 bit, right, then I can hope to get away with it with some probability, with a reasonable probability, right. But in that case the information that I got is also very little. Now one might argue that if she even messes with a single bit and it goes sort of unnoticed, then this means that the two parties do not agree upon the same key. This could happen, right. So if if her disturbance is not caught by us, that means that she has messed with some bit along the way, right, and Bob has therefore decoded it wrongly. In this case, Alice and Bob have a string that differs by 1 bit. This is just a hypothetical example. So how will we correct for that? I mean, does this mean that the entire protocol is dead? Yeah, so from the phrasing of my question, it's clear the answer is no, but of course I am asking you why. What can we do? Something like error correction, like there are various ways that we have to resolve small differences. But the point we are trying to make is that if there is only a little bit of disturbance, then she also gets only a little bit of information and the error that is caused is also quite small. Yes, I am being hand wavy here. The hope is that that is something we can correct, for example using error detection, error correction, something like that. On the other hand, if she disturbs a lot of bits, right, then the chances that she will get caught are higher, because when we reveal those positions where we compare our bits, at that time there should be a good probability of having bits not match. So if I have a certain bit and Bob has decoded a certain other bit, right, then we can guess that Eve did some measurement in the middle and that is why this is not working out. Yeah. So he's suggesting a nice idea that one thing that the two parties could make use of are cryptographic hashes, which is that let us say that whatever bits I have, I hash them and publicly announce the hash, right, and then when Bob receives his bits, he can also hash his bits and check if the two hashes are the same. So I like that you're reading more cryptography, that's great. We have to be careful. So one thing is that we have to be careful from the quantum point of view. So that is one small thing. Another thing is that let us say the hashes don't match. So even if there is a little bit of error in the channel, the hashes may not match, right. So the hashes in fact will not match. I mean, unless you have like some really special hash which is hashing neighboring points to the same value or something like that, in general the hashes will not match. So we have to just be careful about what to do, but indeed that is a standard method of testing integrity of messages, and some such technique can indeed be used. What we are using right now is the most simple one, which is just that I'll just announce the bits and announce some fraction of the bits and hope it's correct. Okay. So but yeah, so we could use something like that. So now what I wanted to talk about was what is the best strategy of the adversary here. So this is just an intuitive argument. I mean, you know, I can write 0 as you know, cos 0 0 plus sin 0 1, yeah, and I can write plus as you know, cos pi by 4 0 plus sin pi by 4 1. Okay, this is just by definition. So it turns out that the most effective thing that the adversary can do is measure in a basis where which lies between the states. Okay, so let me write it and then we will talk about it more. So Eve can measure okay, and the reason that we are choosing this basis is that this is midway between 0 and plus, right, and this is midway between 1 and minus. Okay, here I am ignoring global phase, so it will be yeah, so minus and negative minus I will treat as the same. So you can convince yourselves of this. I already wrote, you know, 0 and plus in terms of like cos something times 0 and sin something times 0. So you can see here, right, that this is 0 and pi by 4, right. So this basis vector will sort of lie in the middle, right. So this turns out to be the most effective thing to do. So now if I want to figure out AI, I want to figure out the bit that Alice sent, right. If I measure using this basis, can you tell me what is the probability that I will get AI? So what is the probability that Eve gets AI? It is the bit that Alice sent. So I am looking at a given bit AI, okay. Alice has sent AI, right. If AI is 0, then she has sent either 0 or plus with probability half each. If AI is 1, she has sent 1 or minus with probability half each, right. And I am claiming that the most effective thing for Eve to do is to learn AI is actually to use this basis, which is sort of in the middle. This is, you know, the most effective way for her to learn AI. So if she measures whatever bit she received, if she measures using this basis, what is the probability that she will learn which bit was sent? So the question is, I mean, in the first case, take the first case, right. So if AI is 0, then basically you have something which is between 0 and half, right. You have a mixture of 0 and half, it is either 0 or half. It is either 0 or plus, I am sorry, yeah, it sounded wrong to my ears even. So it's a mixture between 0 and plus. Now I am measuring with this basis, right. So what is the probability that I will figure out what is AI? Okay, I want a number here. I mean an expression. So, I want some expression here. Okay, so it's going to be cos pi by 8 the whole square. Okay, so this turns out to be roughly 0.85. Okay, but if she does this, so you know she has performed a measurement along this basis. So, the fact that this basis is set up so that you know it is halfway between the states, that is intuitive, right, because if you bias it on one side then you suffer on the other one. So, if she does this, you know, she learns AI with some probability, but the state will now get disturbed by an angle of about how much. So, now you measured in this basis, this changes the state by how much? About pi by 8 radians, right. So, you will now change the state by about pi by 8 radians, and therefore, when Bob does the measurement, okay, then Bob gets a different bit with some probability related to pi by 8. Okay, so I will just write it down. Okay, so the measurement disturbs the state by angle about pi by 8. So, if Bob uses the same bit the same basis as Alice, so note that if he does not use the same basis, then anyway you know we do not have to analyze it, but if he uses the same basis, then we want to say that you know he should get something different, right, because then it will be caught if this bit is chosen for the reveal phase, right, which itself happens with probability half. So, if Bob uses the same basis as Alice, then his probability of recovering an incorrect value okay. So, there is some probability of him recovering an incorrect value, and actually you know this is all I want to say about the security. So, it is just a very high level intuition of you know this information disturbance trade off, that you know you can try to do something to get information about the underlying bit. In this case you know one strategy is that you simply measure it using the most effective basis. This will give you the most information about the bit, but then it results in a probability of disturbance which you can hope will get caught. So, if the sequence is long enough and if her disturbance is high enough, then you will catch these errors. The question is that you know, even if let me rephrase your question, even if she gets detected, isn't this still a form of attack? Because isn't she making them waste time and resources? So, in cryptography we call this a denial of service attack, and this is in fact in real life it turns out that this is actually a very significant attack. So, this is the question. Does anyone have an answer?
It might be, it could affect the time it takes to get this done, but it does not affect the information theoretic proof.
Very good. So, in fact he is right. So, again I will rephrase the answer. The answer is that this denial of service attack is not in the model of security that we are considering. So, see this is actually an important point. When we talk about security of any scheme, right, there is a certain model, there is a certain definition of security, and we are trying to satisfy that definition. Now this definition does not capture every possible attack that may exist in the universe. So, and that is not a bug, that is actually a feature. So what we hope to do is to say that, think of Lego blocks, like we are trying to build primitives of cryptography, piece by piece. Yeah. So each piece I wanted to satisfy some kind of security, right. This is not to say that this is the only type of security that is relevant in the real world, right. But if I get it to satisfy this kind of security and something else to satisfy a different kind, then later when I have an application which may have a complex security requirement, then I can hope to combine these in a meaningful way and prove that all those requirements are met. So your denial of service question, in reality, if this is all you do, right, then indeed, Eve can make them waste time and resources. But in the security model that we are considering, we do not think about that. So as long as they detect her presence and they discard the session, right, we consider that a good case. So that's a very good question, but that's more it's more a question of how you model the security of a given object. And this is a very delicate thing. Actually, when you study cryptography in more depth, these all things become very relevant. So we have not seen a whole lot of it, because really speaking, in like the cryptography aspects that we have seen have all been just about key agreement and encryption, right. So we have seen very little, we have had very little chance to think about many other aspects of cryptography. Like you talked about integrity, right, hashing. So that is a form of message integrity, right, that the message was not tampered with, right. There are questions of authentication. There are all kinds of security considerations that one might have. But yeah, we are looking at some very, very basic security goals right now. That's a very good question. No. So the question is, when we talk about a quantum channel, are we transmitting qubits or are we converting it somehow to classical bits and then sending those? No, we are talking about qubits. Only then does any of this theory make sense, right? If it is, if you have classical bits, then what edge do you have over classical cryptography? Okay, good. So the question is that, here we are saying that Eve is going to measure a state and then transmit that. So won't no cloning be applicable? So all the laws of physics are always applicable, right? So the question is, are we saying something in contradiction to that? And we are really not, right? Because see, measurement using some basis is allowed by quantum physics itself. So you measure using that basis, right, and you get one of the basis states with some probability, and you can send that along, no problem. Why even think of it so much? You can prepare your own quantum state and send it, right? I mean, forget about disturbing. See, disturbing we are doing from the point of view of trying to learn what is happening, right? And even simpler but possibly more pointless thing is that I generate my own stuff and send it, right. So those things are always possible. No cloning does not contradict that. No cloning, we actually spent quite some time in the beginning of the class also saying basically a classical bit is also a quantum bit, right. So you can always clone classical bits, but no cloning is just saying that an arbitrary quantum state cannot be cloned. That does not mean that you cannot measure it or do something else. Yeah, but that is also a very good question. So getting the intuition right for this BB84 is really important, because intuition is all we are doing for this right now, right. So I really hope that the intuition is clear. Yeah, so it's really cool, and both Brennett and Bresard very recently actually won the breakthrough prize in physics or something, for the work that they did in quantum information, right. So it's again one of those things like really good science, where basically you can see it seems very simple in hindsight, You know, that's one of the marks of really good science. So you see how it is really using this idea that messing with a quantum state in any way is a time critical thing. Once it is gone, it is gone. So she is revealing later on what basis is being used, right? But by that point it is of no use to you, because you needed that information simultaneously. And if you didn't have it, then at this stage there is nothing you can do. The quantum state, it was sent using an arbitrary basis. If I know the basis, I know how to decode it, right? If I don't know, then I will make some mistake, and with some probability, and that will again with some probability get detected, right? So it's really clever that you use this temporal aspect, that I am giving you, like from the point of view of classical cryptography, right? I cannot tell you how novel that is. The students here who know cryptography will agree. It's very novel. You typically never give information like this, right? But here it's okay to do it, because by the time the information is given, it's useless to the adversary. Hello, my name is Shweta Agarwal and I'm here to tell you about this course we're offering, Quantum Algorithms and Cryptography. So cryptography is the science of keeping secrets, as you know, and at a very high level there are two properties that any cryptographic scheme needs to satisfy, namely functionality and security. Let's take the example of an encryption scheme. At a high level, functionality means that if I encrypt something, then it should be decrypted correctly. And security means that without having the decryption key, no one should be able to learn anything about the underlying ciphertext. So both these properties must be satisfied. Now if we take a step back and think about how these properties can be satisfied, we come across the following requirements, which are often in tension with one another. For correctness or functionality, we require some kind of structure in the underlying mathematics, and for security we require there to be some computational problem that remains hard despite the structure that we imposed in order to satisfy correctness. And balancing this structure and hardness is the entire field of cryptography. So as we are seeing, the computational hardness or the source of hardness is at the very heart of cryptography. And when one talks about hardness, then one has to specify the computational model. And at a high level, we can think about hardness in the context of classical circuits or quantum circuits. So what are quantum circuits, or what are quantum computers? This is a fundamentally new paradigm of computing that harnesses the laws of quantum physics rather than classical physics, and these can offer an exponential speed up over classical algorithms for some problems. When we study quantum computing a little more closely, we find that quantum computers or quantum algorithms have really this one extra superpower that unfortunately strikes at the very root of the structure that we were imposing in order to get our functionality in cryptography. So what we'll study in this course is how quantum computers work. First of all, what is the mathematical model for quantum computing? We'll see some algorithms that offer speed ups over classical algorithms. Then we'll study some classical cryptography. We'll see this tension between structure and hardness in classical crypto systems, number theoretic ones like RSA and discrete log based. Then we'll see how quantum algorithms can, as I said, strike at that at that mathematical structure and offer a speed up that makes these schemes insecure. Having seen how to break number theoretic cryptography, we'll spend some time trying to recover from this break. So we'll look at mathematical problems that are conjectured hard even for quantum computers, and then we'll try to build some cryptography from these computational problems. In particular, we'll take a somewhat close look at lattice based cryptography. After that, we'll also spend some time looking at whether quantum computers can be used not just to break cryptography but also to build it in ever more secure ways. So then we'll spend some time looking at using some unique properties of quantum computing like the no cloning theorem to see whether we can build useful cryptography from this. In terms of prerequisites, we do not assume any knowledge of quantum physics, so the course is self-contained. We also do not assume knowledge of cryptography, although it is good if you have a little bit of familiarity. We do require a good working knowledge of algorithms and computational complexity. Particularly, you should be familiar with the notion of reductions and how they work. And looking at the course, there are multiple aspects that we cover, each of them not in too much detail due to constraints of time. So we look at quantum computing, we look at classical cryptography, how it's broken by quantum computing, we look at post-quantum cryptography, and we also look at how to use quantum computers to build cryptography, so quantum cryptography. We don't get to spend too much time on any one of these topics, but my hope is that seeing these topics from this perspective can offer us some new insight as to how these systems can be designed and be shown secure. Thank you.